In the last lecture, we have seen the importance of impedance matching at microwave frequency. Now, in this lecture, we will try to learn how to design an impedance matching network with lumped elements. You know that we are familiar with lumped elements due to our low frequency network knowledge. So, up to certain frequencies, typically up to 1 gigahertz, lumped elements can be used for designing, but if we go at higher frequencies, then these lumped elements, their behavior starts changing. You know, the same element like a inductor, if we go higher and higher in frequency, an inductor also have some stay capacitances and other things, so that its behavior may become less inductive, sometimes even completely become capacitive, etc. Like in our labs, if you do any experiment with a lumped element and try to change the frequency of the source that you excite this component with, you may see that sometimes it becomes capacitive, sometimes it becomes not at all resistive, simply a resistor type of thing. Same with capacitor, etc. That is why at higher frequencies you cannot depend on these lumped elements. That time you need distributed circuitry to have these effects of L and C, etc. So, that we will see in the next lecture. So, this one is lumped element based impedance matching network design, and in many practical cases that conjugate matching, we have seen that it is ideal of impedance matching. If you can do conjugate matching between source and load, you can do many things. So, achieving both these gamma s, that means source reflection coefficient 0 and also the load reflection coefficient 0 by making the source and load impedance conjugate to each other. Now, that always is not at the hand of the designers. So, a designer, he or microwave engineer, he should be able to do that given a load and source, but always he can do put a network in between, that is called impedance matching network, and that network will do the job of impedance matching, that we call impedance matching network. So, he should be able to insert a network between source to load for giving this thing. This is called impedance matching network. You see that in the impedance matching network. So, there is a input impedance, there is also, you see that there is an input impedance here. Similarly, there is a output admittance of the impedance matching network. Now, these two he should try to conjugate match, so that source impedance and input impedance Z in, they should be conjugately related. Also in the output side, the load impedance and the output impedance, they should be conjugately related. Then between load and impedance matching network, you will not have any mismatch problem. Between source and the impedance matching network input, you will not have any mismatch problem. So, this impedance matching network design by lumped element we will now learn. So, you see basically the whole thing now has 3 sub impedance matching loops. The first sub thing is the old source is now replaced by the new source, and the whole source is looking at impedance matching network plus the old load network, the whole thing is now looking. So, what is the, but as we have already conjugately matched this source impedance and input impedance of this impedance matching network. So, there we can use that expression that P in will be now, you can see that time we have derived in the previous lecture that in the conjugate match case, the power that is delivered to the resistive part of the load impedance, that is the V A square by 4 R L that time we said. Now, here in the input side this first sub impedance matching loop, that will give us P in is equal to V A square by 4 R in. So, you see that this is same as what power is having at the resistive part of the source, the same power you can deliver at the input of the impedance matching network. Then this is the second sub impedance matching loop as can be seen. Now, nothing special about it. What happens to the third sub impedance matching loop, the source side, there you can see that PRS that has gone as P in the first sub impedance matching loop. Now, that power is again coming as P out and that is getting delivered at PRL. So, the source's total power, half of that is getting delivered to the load. So, this is the same case as the direct conjugate matching. So, with this introduction of impedance matching network also you are achieving the same thing, that half of the source power is PS, half of that is in the source resistance, half of that is in the load resistance, that thing you are achieving here. Now, this impedance matching network IMN, they can be constructed from either passive or active components. Now, there are good impedance matching network, they can be done with active elements like transistor based, emitter follower, source follower, buffer, they are the active element based IFN. Now, problem with active IFNs is obviously any active device, it is having much more change of states, electronic states, and that is why the noise of the whole thing increases. Then any active device is much more costly than passive devices. So, cost is increasing. Obviously, the any active device has a linearity limit, that is why linearity also degrade, and active devices many times have non-linearities. So, you will have to be careful about that, and current drain also increases in case of active devices, because they have these active devices, they draw lot of bias currents etc. So, that is why it is preferred that if you can, if your purpose is served by doing the passive IMN, then that is advantageous. So, in passive IMN again you can make it with RLC, but resistor is generally not used, again that it has some power dissipation. So, that is why if you can avoid it, it is good. Also resistor again is a bit of noisy device. So, generally resistor is not used for passive integrated matching networks. So, mainly passive IMN, by that we mean LC networks composed of either L or C. Now, if the L and C are ideal, as I said that this assumption is up to a certain frequency, after that frequency you cannot call them as ideal thing, but within that frequency range, that means typically up to 1 gigahertz, you can say that LC, you know, they are reactive elements. So, no power they dissipate in there. So, P in and P out are same for them. That is why in the impedance matching network we get whatever you are giving as an input power to the impedance matching network. If it is based on LC, this passive thing, the same power you can take out, there is no dissipation in the L and C. Now, so you ensure the maximum power transport, no phase shift in signal voltage here also. Now, generally if you want to have a amplifier, that time instead of one impedance matching network, you can also have two impedance matching network, because of a transistor, that in transistor you know that it is a input and output, there is a linkage between them. That is why one single impedance matching network cannot always make the whole impedance matching there. So, because of the coupling between the input and output, you know that either it is a 3 terminal device, any transistor. So, which one you call input and output, one of them is common. So, input and output there is coupling, that is why you need an extra level of matching network, generally they need 2 matching network, but we will not talk of this in these lectures. This is a designer of a microwave amplifier, he should know that how to do it, it is a more involved study. Now, basically we will see that if you are designing an impedance matching network, now LC based, there what happens that L and C, they are impedances, they are frequency dependent, actually they have reactances which are frequency dependent. So, we can say the impedance of the matching network, that is frequency dependent. So, it is at a particular frequency this match is achieved. Now, if you give a signal, generally you see any signal, our baseband signals, that composes of various frequency signals. It is very rare to get a single frequency, like when I am speaking various sinusoidal signals are coming up. So, it is a mixture of various nearby frequencies. So, that means if an impedance matching network is matched at a particular frequency, but if the signal is a bit wider band containing bit wider band of frequencies, what will happen? Will the impedance match holds? So, you see that from this diagram that there is in the Smith chart, if you plot the impedance, now if even with change in frequency the impedance does not change, it is rock solid at a point, then it is a good impedance match, but as the curve shows that there is generally a variation of like that, a locus of this as we vary the frequency. Now, obviously that variation of impedance, that should not be much, because then the purpose will be lost, because we are trying to get a particular impedance from this impedance matching network. So, that is why we define that what is narrow band matching. Narrow band impedance matching means the relative bandwidth, which is nothing but bandwidth, that is maximum frequency to which the network can be subjected minus the minimum. So, that bandwidth divided by the center frequency, that relative bandwidth is within 15%, that is called narrow band design. At the end of this week's lecture, we will see wide band impedance matching design, where much wider band of frequencies, that means a much wider signals which containing much wider band of frequencies, they also can be matched with that impedance matching network. Now, one thing is you can plot that, suppose always the reflection coefficient, even if you cannot make 0, you can make that okay, I will make return loss up to certain level, as we see in the previous lectures that okay, I have so and so return loss, the so and so reflection load reflection coefficient. So, power loss is this much, okay, that let us say tolerable. In that case, we can decide that what is the maximum load reflection coefficient you can suffer. That means, return loss is defined as 10 log voltage reflection square magnitude square in dB scale. So, we can plot it, because if you have reflection coefficient, that means our in Smith chart thing, it is U plus JB. So, the power reflection coefficient, that will be gamma is equal to this capital gamma into capital gamma star is equal to U square plus V square. So, in the Smith chart thing, now consider Smith chart as a UV chart, it is a reflection coefficient chart. So, U square plus V square will represent circles, family of circles with center at 0 0 and radius a, radius given by the gamma magnitude. So, you can plot locus various circles of various return losses and see that whether that your impedance points, they are within that circle. If they are within that circle, you know that okay, that return loss is manageable. Like in the previous one, when you see that it is varying, now you can always see that okay, suppose I have also a requirement that frequency may vary like this, but return loss should not vary more than this. So, if we this graph, if we superimpose on that return loss given circle, from there you can see how much maximum return loss you can suffer, and from that you can say that whether this design is okay or not. So, this is called return loss limitation. So, impedance matching by return loss adjustment. Find acceptable RL level, draw the circle, it cuts real axis as 2 points. So, those two resistances are the extreme points beyond which you can need not go. Now, this whole thing, that how much is your return loss of any impedance matching network, you can use network analyzer. We will study network analyzer later in this series of lectures. So, in network analyzer you can connect the input port or output port of the impedance matching network, and you can find various scattering parameters, that also we will study later. By that you can find out that what is the behavior of the impedance matching network. So, with the help of network analyzer you can study impedance matching network. Now, let us come to the passive IMN design. So, there are various things in their terminology. The one arm means generally a series element. So, it can be an inductor or a capacitor. So, arm means a series arm, branch means a parallel branch. So, that also may be L and C. So, that means you can have either an inductor or a capacitor in series, a inductor or capacitor in branch, etc., various combinations of that. Now, let us say that IMN built up one part in series. So, in that case, suppose Z naught was the previous impedance, with that you add one part. So, Z becomes the new way. If it is in series, the extra delta Z is given by that extra arm. So, for L and C, delta R is equal to 0. So, you are adding that delta Z. Now, frequency response of a series L or C, you can see that varies like this. This is the frequency response. So, for inductance it is linearly varying, for capacitance it varies not linearly, it is a hyperbola type of variation, and you know this frequency response is known. So, in the Smith chart how that will vary, we have seen the capacitance and previous day. So, suppose P is a point, you see the this mouse is not stable, this P. Now, this point P, suppose my point, with that it is before I join the impedance matching network or before I join the series arm. Now, I add an series thing. So, if it is a series inductor, that means the inductance value will be more. So, positive reactance will be more. So, from the Smith chart you know, basically that means I will move on the constant resistance circle, but I will move clockwise and get a higher value of reactance. On the other hand, if the series arm is a capacitor, then I will come down, that means I will move in the anti-clockwise direction. So, that is shown by CS direction. So, series arm makes a clockwise for L movement, anti-clockwise for a C arm. Now, similarly, the branch may be in parallel. In that case, the new admittance will be the old admittance plus delta y, and for L and C the conductance change will be 0. So, this is their frequency response of the branches, this also you know. Now, in Smith chart, this means from the point P, from this point P, if I have a parallel branch of inductance, it means I am going in the anticlockwise direction, whereas for a CP parallel capacitor in parallel branch I am coming clockwise. Now, that means that in this the previous two pictures are put here. So, the point P you try to see, this point is the point P. So, this if there is an impedance, now the impedance matching network is either adding either an R or L or C, any of them, a single one. So, if it is a single element L, it is a movement in the clockwise direction. If it is a CS, it is in the anticlockwise direction. So, you see various pull directions here. Now, based on that, the point is that from one point P, suppose that return loss is not acceptable, I want to come closer or lower return loss circle. So, with the help of this impedance matching network, I can be pulled to various impedances. That is, this diagram will help you that which one to add, whether to add an LS, RP, you have various choices, but where it will be pulled you can easily see here, and so you see whether that is acceptable or not, etc., whether you are getting an increase of return loss or decrease of return loss. Obviously, your goal is by this pulling, if you can come to the center of the chart, so that that will be the match, that is the conjugate match case, that there is no reflection there, because center of a Smith chart means the reflection coefficient is 0. So, by this pulling you can come to one part or other. Now, one with a single part, this impedance matching network, this is problematic, because small chance of pulling impedance to center by single part, because only in one direction you can pull by a single element. Original impedance should be on R is equal to 1 or G is equal to 1 circle, then only you can do a perfect conjugate match with these. If the original impedance is not on constant resistance or constant reactance circle, then by pulling alone by a single element you cannot do that. But the whole game changes if we use, instead of one part, two part impedance matching network. So, narrow band impedance matching with two parts is more practical. Generally that is called L section, actually L, but to pronounce sometimes it is EL also called. So, basically in an EL section you have one arm, one branch, that means one series element, one parallel element. Now, so there are 8 such possibilities of L section. You see that you can have all the right side is the load. So, you have either a series C, both the series and parallel, that means the arm and branch both are C, both are L, the first one L, the second one L, or various combinations. So, there will be 8 such combinations as a senior. So, 8 L section matching networks are possible. From that you can choose. Now, which one to choose at which point? For that, actually the Smith chart is divided into 4 regions, as you can see. How the regions are defined? All these regions, suppose region 1, that means if you are having in the admittance chart what we call 1 plus JB, that circle, that means the left part of the Smith chart where it is passing through center as one periphery and the left end of Smith chart one periphery. Then if you draw that circle, that is region 1, the region 2 different shading is shown, which is generally our 1 plus JB circle in the standard impedance Smith chart. similarly the 3 and 4 you can see. Now, based on your original impedance, that is at which point you decide these things. So, if you are your original impedance, if it falls on region 1, then you will have to take one strategy, then region 2, region 3, region 4. So, your first impedance at which point, depending on that you can choose one of that 8 ones. Let us proceed. So, here we have seen that these 4 regions on Smith chart, region 1, region 2, whatever we said. In region 1, basically we have the R is less than 1, R means the R bar, X is X bar, etc. So, that is low resistance part, region 2 is high resistance part, region 3 is low resistance as well as low conductance, and region 4 low resistance and low conductance. So, based on that these 4 regions. Now, this is the thing that region 1, if I am in region 1, again P, now we are calling, since it is region 1, P1, that means the original impedance is here. Now, finally, I want to come to the center of the chart. So, I have 2 ways, either I can be pulled like this and then I come to the center. So, you see again I am doing that from P1 I will be pulled. I know that by one element I can be pulled in various ways. So, I will be pulled, I will be pulled from here to top, I will touch that 1 plus JB, that circle, it is reflected one, this constant one circle, and from there I will come to the center. Or I can, instead of that, I can also from here come like here up to this, and then I can be pulled to the center. So, I have 2 such alternatives. The first alternative, now again if you go to that single part there, how the pulling is. So, if I want a, by a single part I want a clockwise pulling, I should have an LS in the series arm, and then if I want a clockwise pulling, that should be in a parallel branch, it is a CP. So, that is why the first circuit in the right part, that LS CP is my choice. Or the second one means I will have to be pulled like this. So, you can see that if I want a this anti-clockwise movement pulling, then I need a CS in the series part and one parallel LP. So, either this or this second one is my choice. Now, it is up to you which one you choose. We will see that the frequency response of these two are generally different. So, from that you need to plot the reference and see. Generally, the one rule of thumb is try to see that which one gives you the lower values of those L and C. That means, the when you are getting pulled, do not get pulled by much. So, the minimum path that you can take, but still that is a rule of thumb, always it is not valid. More meaningful is you can always plot the frequency response and try to be as better or wide bandwidth things by choosing the one which gives you more. The same thing in region 2, if you are originally in region 2, that means in point P2, you see that in 2 ways you can be pulled. From P2 you can either come down to point D and then from D to DO, or from P2 you could have gone to C and then C to O. So, again by looking at that final graph of one way thing, that means this one, this actually helps you to tell that which one you are getting pulled. So, which element to choose. So, from that people have already found out that for region 2 you have these 2 choices, same thing for region 3, you can be from P3 you can either come to C and then to O, or you can go to B and then O, depending on that there are 2 choices. region 2 4 choices. So, if you summarize that common steps in all this, step 1 is pull the original impedance to either a G is equal to 1 circle or R is equal to 1 circle, which one is appropriate depending on your position. Then in the next, by the next part of the component, you get pulled to the center. So, the first part of the component that brings you to either a R is equal to 1 or G is equal to 1 circle, and the second part brings you to the center. So, one part will be always in series, another part is in parallel. Now, it is up to you to select whether the first part you want as series or parallel. So, you see all these designs, whether the first one, that means from load the first connected one, that is in series or parallel, that is your choice. You see all these are different in these two, but which elements, that is up to you. And you see that if your original impedance is in region 1 or region 2, then two parts, one of them will be L, another will be C. That is why I have given this heading. You see LC, LC. So, first and second region, they will have your choices, both the components are opposite, LC or LC. Whereas, if you are in region 3, then both parts are C. If original impedance is 4, then both parts are inductances. Now, so you can decide 8 possible topologies, and so this you see that if you choose. So, this is another thing, that in certain cases you cannot always, it is not guaranteed that by this 2 1 you can get a proper impedance matching, that means always you will be able to come to center, that is not. So, here is a list that will help you, that if you are in region, the first column, first means second column says that if you are in those regions and you choose the topology that is in the first column, then you will be able to come out. But if the third column says that if you are in region of those regions and you choose that corresponding topology, you will not be able to come out. Those are called prohibited regions. So, if you are in prohibited regions, by that topology you cannot come out. So, that means, and also some other considerations is that topology 7 8, topology 7 8 means, you see here 7 and 8 means both the components are inductance. Now, fabricating an inductance is difficult at high frequencies, also inductances are costlier than capacitances. So, 7 and 8 generally people avoid, that these are costly. Then DC blocking, DC short circuiting, DC feeding, these are also other things, because capacitors sometimes are used for DC blocking, etc. So, which one you will if you do not have capacitors, DC blocking may be problem, etc. L, you know that if you have both L's, you can have DC short circuiting, etc. So, based on that. So, now prohibited regions are limitations of two sections matching. So, always it is not guaranteed that you will be able to come out by any topology, but if you choose the proper topology, then whatever way we have shown, you will not be in the prohibited region. So, you have some choices there, but it is a limitation that by two parts you cannot have always a match. That is why 3 parts are better, that impedance matching network built of 3 parts. These are all the possible topologies we have listed. We are not going here, just for your reference, if any of you attempt it here, then you can see that there are some of the cases like the topology number 3 and topology number 3 in both the pi type and T type, there are no prohibited regions. So, all possible wherever you are in the Smith chart in the original impedance, always it can be matched by these topologies. Okay. So, in this lecture we have tried to see the L section matching, that means by LC network how to do the impedance matching, so that you can put an impedance matching network if the source and load they are not in your hand, they are impedances, but you want to make a conjugate match for them, you can put proper LC network. So that source will also see that okay, it is seeing a conjugate matched network. Similarly, load will also see that the impedance matching network is developing, giving me the conjugate matched source. So, both the power transfer can be there. Internally inside the impedance matching network, there may be reflections and things. We are not bothered about that, because our job is transport from source to load, that is achieved by impedance matching network. So, this is about passive, using passive components to do this matching. In the next lecture, we will see how we can use distributed components to do the same type of matching.